Okay, so with my new blue light glasses, and we are going to do a recording of the first part of the energy and enzymes, um, ugh, the energy and enzymes PowerPoint that I will post. Oh no, I tried to share my living room. Sorry. All right, so here is the PowerPoint. Note that we are talking only about part of chapter 8, right? So we've done tour of the cell, chapter 6, membrane transport, chapter 7, and then only part of chapter 8, which is 8.3 to 8.5, which has to do with energy and enzymes. And again, Khan Academy and Mr. Anderson have great videos for this, which I will post. Okay, so we're starting with metabolic pathways. So metabolism is defined as all of an organism's chemical reactions, all of them. It's a whole lot of chemical reactions, all right? And those reactions can either be catabolic or anabolic. So catabolic releases energy. So you're gonna get energy out, right? So energy out is catabolic. This is breaking things down. So when you break things down, going from complex to more simple, you get energy out. A good example of that is when we have our polysaccharide glycogen. Remember, that is a long branched polysaccharide. It is very complex. When you have a catabolic reaction, that is, for example, breaking that down to give off glucose, and you're also going to release energy. The way I remember that is, I don't know, this is so stupid, but I don't know why it always remembers me. Why I always remember it this way. Break the cat, right? So catabolic, you're breaking things down. Cats are very energetic, so you release energy, right? Anabolic pathways, on the other hand, consume energy. So they are going to take in energy. They, in another word, in another way, they require energy, right? They require energy. So this is to build up things, going from simple to more complex. For example, having two glucose molecules come together to form a disaccharide, that is anabolic. You have to add energy in there to create these bonds, right? So catabolic, breaking things down, releasing energy. Anabolic, building things up, requiring energy. And when we're talking about energy, we are always going to be talking about our friend, that nucleotide called ATP, adenosine triphosphate. So this is a picture, right? This diagram here represents all of the metabolic pathways in the human in a cell, right? And you can zoom in, and it's crazy, right? So there's a lot. We are going to be focusing in the next section on one itty bitty little part of that, which is in here. But in general, I just want you to know that there are literally thousands upon thousands upon thousands of reactions occurring within a cell at any one point. These metabolic pathways are very complex and very interconnected. We're going to focus on just a small part of them. But this always helps me kind of think that every time we are dealing with a living cell, each cell really is a miniature chemical factory with thousands of reactions occurring at one point, right? So this is kind of a blow up of part of the reactions that you guys are going to know. But just remember that metabolism really is all of those occurring at the same time, right? So to truly understand energy, we have to understand the first two laws of thermodynamics, which I think you learned in physics a little while ago, but let's review. So for thermodynamics, the first law of thermodynamics is that energy can neither be created nor destroyed. So energy before and energy after are always going to be equal, right? Before and after a reaction, the amount of energy is the same, right? Energy can neither be destroyed nor created. The second law of thermodynamics is that entropy, and when I think of entropy, I think of disorder. Entropy tends to increase in the universe, or disorder always increases, right? And you guys have experience of this. Think of your rooms, right? This is my son's room. Well, this is not actually my son, but this is like my son's room every morning. I make him clean it before he starts online school. And then by the end of the day, it spontaneously becomes a crazy mess. In other words, there has been an increase in entropy or disorder. And it takes a lot of energy to get back into that organized effort or in that organized effect, right? So it takes energy to get things to be ordered and nice, and everything tends towards disorder. And then you have to put energy to make it ordered, and then it tends toward disorder. So in biology, energy is often lost as heat, right? Heat can be defined as thermal energy. It's associated with the random movements of atoms or molecules. And what I think is most important here is that heat really is the energy in its most random or disordered state, right? So heat is energy in its most randomed or most disordered state. And again, that would be with very high entropy, right? Because entropy is kind of disorder. So what these mean is that basically the first and second law of thermodynamics together, they kind of define that the quantity of energy is constant. The amount of energy doesn't change. However, the quality of it does. So let's look at this leopard here. So this leopard is consuming its energy by eating this gazelle. That is in the form of chemical energy. So it's eating the chemical energy stored in that deer meat. And then as it's running very, very fast, it is losing some of that energy to heat, right? And in the process of losing that energy, it is getting rid of waste products in the form of carbon dioxide and water. What it consumed was oxygen and glucose, right? So in the next section, we're going to talk a lot about that process called cellular respiration, where organisms take in oxygen and glucose to give off carbon dioxide and water. But again, for thermodynamics, the quantity of energy is constant in any reaction, but the quality is not. And very often, we, as organisms, lose our energy in the form of heat, the most disordered state of energy. All right. So energy. Energy to do work. So we know our cells have to go through thousands upon thousands of reactions for their metabolism. And so in order to do those reactions, we need energy. All right. So free energy, we are going to define as G, right? And that stands for Gibbs free energy, Gibbs. It's an old white dude in physics. And free energy can be defined as the energy that can do work, for example, in a living cell. All right. The change in free energy, move my face a little, we're going to define as delta G, the change in free energy. And only processes that have a negative delta G are spontaneous. So let's look at that just in terms of a ball rolling down a hill. All right. So if we have on the y-axis here free energy, so we have our Gibbs free energy here, and we have the course of the reaction on the x-axis. Here, a ball rolling down a hill starts with free energy that is quite high, and the result down here in the products is a G that is much lower, right? So the reactants had more energy than the products, and so that is considered a negative delta G, right? So we went down. In this process, you get energy released, right? So energy released when you have a negative delta G, and this is by definition called a spontaneous reaction, right? In this regard, the ball was going down the hill. Okay? And we're going to talk in a second about how that is considered an exergonic reaction. So if we think of the other way, again, we have G on the y-axis and we have the course of the reaction on the x-axis. Here, we are getting a ball to go up the hill. So the reactants here had less energy than the products, right? So here, this is a positive delta G. The amount of free energy had to increase. Here, we needed to add energy to this reaction in order for it to go. So this reaction, we needed energy. It was not spontaneous. And the example is rolling a ball up a hill. And we'll talk in a moment how that's considered an endergonic reaction, right? So here we have our exergonic reactions versus our endergonic reactions. So let's just define all of these. So exergonic reaction, the products have less energy than the reactants. So again, if we were going to do a little curve with your amount of G and, for example, the reaction here, the exergonic reactions, the products down here are going to have less energy than the reactants up here, just like that ball rolling down the hill, right? What that results in is a negative delta G, which by definition means it's a spontaneous reaction. And here we're going to see that entropy is increasing, right? So exergonic reactions, products have less energy than the reactants. You have a release of energy, a negative delta G, it's spontaneous, and the entropy is increasing. So if we just look at this picture down here, in our exergonic reaction, we are looking at a reactants starting here. So these are the reactants. Here we have our products. We can see that the negative delta G is represented right there, negative delta G. And this is going to therefore be a negative delta G. That's going to be a spontaneous reaction. An example of that is going from glycogen down to glucose, right? And again, this is a catabolic reaction. So exergonic is catabolic, right? Break the cat, you're breaking things down, you're increasing you're increasing entropy, and you're releasing energy. This is spontaneous. The other hand, we're going to talk about endergonic reactions, and these are anabolic reactions, right? And endergonic, the way I kind of remember that is ender, you're taking in, right? Exer, you're releasing energy. Endergonic, you need energy, you're taking it in, ender. So here are, if you look down here, the products versus the reactants. You can see that this is going to be a positive delta G. The products have more energy than the reactants. The energy required is a positive delta G, so by definition, it is not spontaneous. And since we had to add energy, entropy is decreasing. And the example of this is going from glucose into a polysaccharide, such as glycogen in animal cells. So here's something that we're going to talk about over and over again, where we have, just a minute. Yeah, I guess I don't have this. All right, so we have the example here of photosynthesis, and photosynthesis is using free energy from the sun. So we have our little sunlight here, adding free energy. So that's going to be an addition of energy. We are building up, so we're looking at the free energy. Here we're building up to our glucose, C6H12O6. And what we're doing here is the energy from the sun is stored in chemical bonds in the form of glucose, right? Again, the energy from the sun is stored in the chemical bonds of this glucose. So let's review. If we are building up, we had to put in energy. So that is going to be endergonic, put in energy. And at that same time, this is going to be anabolic, and not, this is going to be a positive delta G and not spontaneous. All right. Cellular respiration is the exact opposite, where we're taking the energy stored in this glucose molecule and we're breaking it down through a process called cellular respiration, right? So when we break down glucose in cellular respiration, we are going to see a release of energy. We see that here in the form of ATP, so energy is coming out. This is going to be considered exergonic reaction because we're getting energy out. It's considered catabolic, break the cat, and this is going to be a negative delta G, and therefore it would be considered a spontaneous reaction. So ATP, just to get everybody, make sure everybody's on the exact same board here, same page. ATP stands for adenosine triphosphate. So it consists of a ribose sugar, a 5-carbon ribose sugar, a nitrogenous base, which is called adenine in this case, and triphosphate. So we see 1, 2, 3 phosphates. They're connected by what we call high energy phosphate bonds. When ATP gets broken down, so when ATP gets hydrolyzed into ADP, that is going to be a breakdown, right? So that is going to be catabolic, right? You are going to get a negative delta G, and in this case, it's a really negative delta G, and we're going to see energy released, right? So when we break down ATP, it's called ATP hydrolysis. Remember hydrolysis? So we're breaking one of those phosphates off. So we break down ATP, you get ADP, and you're going to get an inorganic phosphate. And what you're going to see is that you get a release of a lot of energy in the form of negative delta G. A lot of energy. ATP hydrolysis is kind of like the cell's currency for energy. Break it down, you get a lot of energy. So ATP powers cellular work through the coupling of endergonic and exergonic reactions, right? So people get really confused on this, and I'm going to try to make it as simple as possible. So I'm going to start over here with the words. So cells make endergonic reactions happen. So remember, those are the ones that require energy. They make those reactions happen by supplying them with free energy released from exergonic reactions. And the big exergonic reaction that we're going to see is that ATP gets broken down to ADP and releases energy in the process, right? So this idea that you can transfer energy from one reaction to another to drive another is called energy coupling. So again, let's just look at the energy content of the molecules here kind of on the y-axis. And the first thing we're going to see is that we have a catabolic reaction. We are breaking down glucose through cellular respiration, right? So breaking down glucose here, that is going to be catabolic with a negative delta G, right? As we do that, we are going to see that as you break that down, that allows for the creation of ATP, right? So this negative delta G in this catabolic reaction is going to create a lot of energy in the form of ATP, right? That is this is our energy release from that catabolic reaction, meaning we make a lot of ATP, right? Then, as we kind of, we can break that down, and what we're going to see is as we use ATP, and we're going to use it, meaning we're going to hydrolyze it to drive the reaction of other things, such as the building up of amino acids to proteins, or the building up of glucose to glycogen, or the building up of nucleotides into nucleic acids, etc. So all of the building up of those biological molecules, which we know are super important, all is driven through ATP, right? ATP hydrolysis. So ATP drives endergonic reactions through a process called phosphorylation, right? So phosphorylation can be defined as the transfer of a phosphate group to a molecule. All right, so let me just, so here, if we have protein A and we have the addition of ATP, we can use that ATP. ATP is going to turn to ADP, and now we can cause, create a molecule that is called a phosphorylated A, right? So this phosphorylated A, it got that phosphate group from the inorganic phosphate that was released when ATP was hydrolyzed. So ATP gets broken down, you get the release of energy, and you also get this inorganic phosphate. That inorganic phosphate got put onto this protein, right? So that's called a phosphorylated protein. Okay, so if we look only at this top part here, we are looking at a reaction where we are going to build up, so it's going to be anabolic. We're building up glucose and fructose to create sucrose. So this is anabolic. It's going to be endergonic, meaning, again, you need an input of energy. This is going to be a positive delta G. It's going to be not spontaneous, right? So this is the uncoupled reaction. It takes a lot of energy, right? The coupled reaction that actually happens is that it happens in 2 steps, right? The first step down here, number 1, is that glucose is going to interact with ATP. ATP is going to be hydrolyzed down to ADP, and this little phosphate that we lost is going to be added onto our glucose. So now we have a phosphorylated glucose with a little phosphate group. The second reaction is that this phosphorylated glucose is now going to be able to react more easily with fructose to make this sucrose, right? And I'm going to show you that in a little more detail here with these free energy diagrams. So this up top is what the reaction overall would look like, right? Where we have glucose and fructose coming together. Again, we have a positive delta G. This is going to be anabolic. This is going to be endergonic because you need to add energy. This needs energy, all right? So instead of doing that hard reaction, what we're going to do is break it into 2. So down here, the first reaction, so this is going to be reaction number 1, shown here, where the reactants have more energy than the products, right? So here, this is going to be, we're going to be breaking down ATP, right? So ATP to ADP, that's going to be negative delta G. This is going to be catabolic. This is going to be exergonic. You are going to release lots of energy, right? So this has a big negative delta G. We're going to couple that big delta G to this second reaction down here, where it is anabolic, but it's not, sorry, let me rephrase that. Sorry. All right, so those are our kind of those are the 2 reactions that we have. We have one, sorry, I'm going to erase those 1s and 2s. I think they're a little confusing. So we have this first one here that is highly negative or sorry, highly positive delta G. We have this one here, which is highly negative delta G. When you add them together, so you add those two together, you get an overall exergonic reaction, right? And that is because of this coupling. So if you add these together, negative delta G and this positive delta G, this reaction is still going to be a negative delta G, and it's going to be spontaneous, although it's not nearly as exergonic as that middle one. All right. So the whole point of this, I'm not going to, I feel like I belabored it. The whole point of this is that ATP allows the cell to do a lot of endergonic reactions. It is highly exergonic. It allows the release of energy to do a lot of endergonic or building up reactions. All right, and we will stop there for this first part.